Let's study what means and variances look like when there are many random variables, not just one or two, but more than two random variables. For example, suppose there are 5 companies' stocks. Stock in American English or share in British English, either way is fine. So there are companies A, B, C, D, and E. Suppose you're an investor and you're going to invest in these 5 companies' stocks, okay? And you are interested in the returns of these 5 company stocks. So random variables here are stock returns of these 5 companies. So there are 5 random variables in this example. As an investor, you have to think a lot. Like, okay, I have £10,000, I want to invest this money, I don't want to take too much risk, but I want at least 10% annual return for my portfolio. Now, how much money should I invest in each of the stocks? Something like that. For your decision making, what information do you want? You'll never know actual returns. In good states, these returns will be high. In bad states, these returns will be low. You'll never know. But you can still get the information about the average performance of these 5 stocks. In other words, the expectations of the stock returns, or expected returns in short. You can get such information from economists or analysts, which looks like this. Because there are 5 random variables, there are 5 expectations. It looks like this. Aviva's monthly expected return is 1.10%, British Gas 0.9%, Capita 1.05%, Diageo 1.15%, and EasyJet 1.2%. They look very low, but let's say they are monthly returns, so it's like 12% per year, which isn't too bad. Okay, but the point is that if there are 5 random variables, there are 5 expectations. So the whole expectation is denoted as a vector, which is composed of 5 numbers. What's the next thing you want to know as an investor? Probably you want risk information. But in what form? Well, you think there are 5 stocks, 5 stock returns, so I want to know 5 variances or 5 standard deviations. Something like this. Okay, Aviva's variance, the variance of British Gas's return, the variance of Capita's return, and so on. Actually, that is not good enough information for risk. You also need covariances. You see, if there are 5 companies, what you care is not just the risk or variability of individual stocks. You also care how, for example, how Aviva's return and British Gas's return are correlated with each other. Or how much, for example, Capita's return and Diageo's return are correlated with each other. In other words, you want not only variances, but also covariances. So, because of that, if there are 5 random variables, the risk information or variability information is given as a 5 by 5 matrix. Okay? It's not just 5-dimensional vector of variances. The risk information should be given by a 5 by 5 matrix, and this matrix is called the variance-covariance matrix. The diagonal elements of the variance-covariance matrix give you variances of individual random variables. variables. For example, 290 is the variance of Aviva's return, 131 is the variance of British Gas's return, and so on. Off-diagonal elements, on the other hand, give you covariance information. For example, the covariance between Aviva's return and British Gas's return is 96. The covariance between Capita's return and Diageo's return is 15% squared. So you can see that the co-movement between Aviva and British Gas's return is much larger than the co-movement between Capita and Diageo. Note that this matrix is always symmetric. You see 96 here, and you see 96 here as well. And you see 53 here, and you see 53 here as well. And this is because, correlation between Aviva and EasyJet is the same as the correlation between EasyJet and Aviva. Switching the order doesn't change the correlation. And because of that, the variance-covariance matrix is always symmetric in terms of this diagonal line. The vector of expectations is often denoted by Greek letter mu, to emphasize that this is not just one expectation, but a vector of more than one expectations. You can use a bold letter, and that's the expectation vector. To denote the variance-covariance matrix, you can use capital letter V, and again, to emphasize that this is not just one variance, but the variance-covariance matrix, you can use a bold letter. Like expectations, variances and covariances are also something that people can estimate. So you can ask analysts or portfolio managers, and they will tell you variances and covariances for you. If it's something else, such as weather or temperature of, let's say, Birmingham and Manchester and York, then you can ask a weather forecast company, and they will tell you expectations and variances and covariances of tomorrow's temperature. However, as I mentioned in a previous class, variances and covariances are not necessarily very popular measures of variability and co-movement, because they are not very intuitive numbers. So, most academic articles report, instead of variances and covariances, they report standard deviations and correlation coefficients. So if there are 5 random variables, as in our numerical example, they would report standard deviations in the form of a vector of 5 numbers, and they would also report correlation coefficients in the form of a 5 by 5 matrix. So such a matrix is called correlation matrix. Basically, these numbers are correlation coefficients. For example, 0.263 is the correlation coefficient between Aviva and Capita. 0.529 is the correlation coefficient between British Gas's stock return and Capita's stock return. So you can see that the correlation between British Gas and Capita is much higher than the correlation between Aviva and Capita. And finally, remember, as long as you know standard deviations and correlation coefficients, you can always recover variances and covariances if you want them. And if you have variances and covariances, you can always compute standard deviations and correlation coefficients.